start. As we just heard, the first presentation will be given by Romain Soulas, who is the head of project R&D at CEA-INES, the French National Solar Institute, and he speaks on behalf of GoPV about 21% efficient half-cell gapless modules with 40% less ECA. So everything you need to have to make a good module today. Romain, the floor is yours.
Hello, so let me share my screen. So let's try to see if it's working correctly. So is it okay? Can you see correctly the screen?
Perfect, please go ahead.
Okay, nice. So good morning, thank you for this introduction. So I'm very glad to present you a part of the work within GoPV project. So it will deal mainly with the several improvements carried out in this project to reach high efficiency module with a novel architecture. And first, I'd like to thank all the partners in this project who led to the results I will present today. So first of all, a short reminder of why we were using heterojunction cells. So it were used because of their high performances, their very good stability, and also their inherent bifaciality, which is a real asset for the module which will be performed in this project. And another thing is that they are compatible with ultra-thin wafers, which we will see is a good asset for the reduction of the environmental impact. So all the work which will be presented for the heterojunction cells has been performed at our cell lab using the HiPERION facilities, and you will see it's very pleasant. So if we have a greater look at the last top ranking of the module at TaiyangNews, you can see that a small but an important part is for the heterojunction modules, and they can reach a very good efficiency and a high power density. And one of the assets is that they are major part of this module are bifacial. So heterojunction cells and modules are very good for the high efficiency, but they requires a particular interconnection process which requires low temperature. So today we can give two main ways of interconnection or interconnecting them, which is smart wire technology or the use of electrical conductive adhesive interconnection. Both ways require special equipment that we will see in this project where necessary. So in this frame, the GoPV module objective were built. So we were focusing on the use of heterojunction module with 72 equivalent M2 wafers. The module were with anti-reflective and anti-soiling coating, which are better than the commercial ones. And we were focusing on the reduction of the material to improve their efficiency in a glass configuration to have a very high efficiency with a 400 watts for these modules with a low cost of ownership. So as close as possible at 0.22 euro per watt. So in the work package I was working with, we were focusing on the material efficiency and the architecture, as we will see. So our starting point was this initial BOM. So you see what we selected at the beginning an half-life configuration to reduce the serial losses and improve the CTM of the final module. We were using heterojunction cells interconnecting using ECA technology with light capture ribbons to have better performances. And the encapsulant selected was a polyolefin type to have a very good compromise between the properties and the price of this one. So you can see at the picture that one of the many modules we have manufactured, a bifacial one using a glass-glass structure. And to go one step further and to improve this BOM, we are focusing on the reduction of material consumption. So using several ways. So the reduction of the silicon amount by the use of thin wafers, and the reduction also of the silver contents at the cell and the interconnection module level. Sorry. And finally, to improve the efficiency, we will propose a new architecture of the module as you will see. So if you have a look at the standard BB6N2 cells that we are using at the cell lab, which are manufactured, you can see the typical parameters of these cells, so 160 micrometer thick, and an amount of silver, which is quite important, 250 milligrams for BB6 cell, and the bifaciality, which is 90%, and it's inherent to the symmetrical structure of these cells. A very hard work has been carried out to reduce the thickness of the cells from 160 to 120 micron, and to reduce also the amount of silver used by the use, among other things, of thin lines. And you can see that a reduction of more than 30% of silver was possible. This reduction of silver does not affect the cell efficiency, which is a very good step, in fact. And one other thing, among others, is that the use of narrower lines gives the possibility to increase the bifaciality of the cells by 2%. So the cell is a starting point for doing good modules, and this work was very important for us. At the module level, as I told before, this interconnection of the cell requires a special equipment. So our partner, Mondragon Assembly, developed a multi-ribbon taper stringer, which able to handle half of full cells with the use of wires or ribbons up to 10. This equipment is also very nice because it can handle cells very thin, up to 110 micron, without increasing the working rate. And it's equipped with 2 independent cells in printing station, which you will see is very important to reduce the HCl content. Finally, this equipment is also compatible with the use of gapless and paving technology, which will be also very useful for the high efficiency modules. So if you are looking at the HCl reduction we were able to obtain, you can see that we were using several HCl reduction designs. So from our reference, which is a full line with a given width. From that, we were using narrower lines, still using a full line design, which achieve a 40% reduction HCl, and other designs, type C and type E, with 2 thighs of width, smaller, which is the second one, and a normal one, which is a 1. So we were able to obtain reduction of HCl from 40 to 65%. Strings manufactured were put into modules and tested using the normative sequence of thermal cycles up to 400 cycles. And you can see below the results. And you can see that all the modules give very good results in terms of losses, which remains very acceptable. The most aggressive HCl reduction leads to higher losses in terms of power, but it's still acceptable. In GoPV projects, in order to remain quite conservative, we selected the middle reduction, so the 40 to 45% reduction, which will be used in the optimized BOM. Concerning the architecture of the module, we were also manufacturing some string from small gap, at small gap with the interdistance, which is our reference, 2 millimeter to 0 gap. And also using paving with an overlap from 0.25 millimeter to 1 millimeter. So these strings module were built with these strings and tested up to 200 cycles in thermal cycles, sorry. And you can see that at the results before, the losses are really good. In fact, are really small, and that all the configuration could be used for the GoPV projects. You can also see that finally the paving architecture seems to be more stable than the small gap, which was not obvious for us at the beginning. And finally, in the GoPV project, we selected the zero gap architecture to optimize the module efficiency. So finally, if we are looking at the improvement of the BOM, you can see that we have the initial parameter on the left of the screen, which I've talked about a few slides ago. And from each BOM I will present, we will have a look at the CTM, the total module surface efficiency, the cost of ownership, which is an important step for the GoPV project, and also the environmental gain we can achieve with the optimization of the BOM. So with the standard BOM, we have been able to build very good module with a total module surface efficiency close to 20% and a cost of ownership of 0.28 euro per watt, which is quite acceptable, but can be improved a lot, we will see. So if we take into account all the improvement I discussed just before, you can see that using the gapless architecture, we were able to reduce the length of the module. So it was necessary to, it's a good step. And with the improvement at the cell and interconnection level, so the silicon reduction and the silver reduction at the cell and module level, we can increase the total module surface efficiency by 1 point, reduce a little bit the cost of ownership, but what sense? But one interesting step is the carbon footprint reduction by 15%, mainly due to the silicon reduction, and the resource depletion reduction by 30%, which is mainly due to the silver consumption reduction. So this result is very good for us, and we can go one step further. We're still working on that. If we are looking at the more drastic reduction we can achieve, so we are still working on that by the reduction of a little bit more of silicon thickness by 110, and the reduction of silver content at the cell and also interconnection level. So we can use the more drastic ECA reduction with the use of narrower ribbons. And with these new inputs, we can hope to have a very higher carbon footprint reduction and resource depletion reduction, still by keeping the same efficiency of the module. So at the conclusion, what we have performed within GoPV project was to start from a BOM and to make good improvement at the material reduction while increasing the efficiency of the module. So by the reduction of silicon content and silver content and the use of a novel architecture, which is gapless architecture, we're able to keep a high efficiency module and reduce the cost of ownership and also the environmental impact of this. So in the future, there are several steps which can be carried out, like the silicon sourcing wafer in Europe, which will allow us to reduce again more the carbon footprint, and the replacement of some critical materials, mainly indium and silver, which can also help to reduce the resource depletion by even more than 40%. Thank you for your attention.
Thanks, Romain. Very nice overview. Here, maybe two questions. The one question from the audience: did you test the reliability of the module in that project, and particularly the contacts?
Yes, we have tested them on up to 400 cycles, and the results are very good. In fact, one question, maybe it's the other one, is that we are using the polyolefin encapsulant is quite thick to avoid any breakage of the cells, because the gapless architecture can mainly lead to this kind of issue. And in our case, we did not face this issue. So the reliability of our module were tested and very good, in fact.
Okay, okay. Any other questions? So I think maybe on what about, here was one question, what about expansion on contraction of interconnects due to thermal variation? Have you seen anything there?
Some normal losses under the limit of 5%. So up to 400 cycles. We are running the test up to 600 now, but so far it remains very good, in fact. The use of ECA is probably an important step for that, because it's not too rigid. It's flexible as interconnection, so it allows to have some variability and deformation, and without any blockage of either the cells or the interconnection.
Okay, super. I think we continue now, but in case there are any further questions, maybe it would be nice, Romain, if you could also answer in the chat. That would be super. Okay, then let's keep that. Thank you so much, and we continue with the next presentation.